Let's consider some examples. Find the nature of all stationary points of the curve y equal to x cubed minus 12x plus 1. Now to find the stationary points, we would differentiate y with respect to x. Derivative of x cubed is 3x squared. Derivative of minus 12x is minus 12. Derivative of 1 is 0. So we'll set the derivative of y with respect to x equal to 0, and if we solve for x, we obtain x squared equal to 4, which results in x equal to plus or minus 2. So at x equal to plus or minus 2, we have stationary points. Now we need to determine the nature of those stationary points. So at minus 2, we have a stationary point. At plus 2, we have a stationary point, and dy dx at minus 2 is 0. At plus 2, dy dx is 0. Now for values of x between minus 2 and 2, 0 is a value between minus 2 and 2. So if you substitute x equal to 0, the value of dy dx at x equal to 0, if you substitute x equal to 0, we obtain the value. If you substitute x equals 0 in this expression, we obtain the value minus 12. So obviously dy dx is negative for values of x between minus 2 and 2. And if you substitute a value less than minus 2 for x, for instance minus 3 in this expression, we have minus 3 squared is 9 times 3 is 27, minus 12 is a positive number. So dy dx is positive. Likewise, if you substitute a value greater than 2, for instance 3 in this expression for dy dx, we again have 3 squared is 9 times 3 is 27, minus 12 a positive number. So for values of x greater than 2, dy dx is positive. Now to determine the nature of stationary point at minus 2, the gradient is positive to the left of minus 2, 0 at 2. The gradient is negative to the right of minus 2. So clearly at minus 2 we have a maximum. And at 2, to the left of 2, the gradient is negative. At 2, gradient is 0. To the right of 2, gradient is positive. So clearly at 2, we have at x equal to 2, the stationary point is a minimum. Now to determine if there are any points of inflection, we need to differentiate dy dx once more. So dy dx is 3x squared minus 12. So if we differentiate it once more, we obtain the second derivative of y with respect to x, which is 6x, and 6x at x equal to 0, the second derivative is 0. So there is a stationary point at x equal to 0. In fact, it is a point of inflection. So there is a point of inflection at x equal to 0. Now when x equal to 0, the value of y is 1. So 0, 1 is a point of inflection. And at 2, when x is 2, we have 2 cube is 8. So we have 8 minus 12x, so 8 minus 24 plus 1. So let's write it down here, 8 minus 24 plus 1. So the value of y when x equal to 2 is 8 minus 24 plus 1, which is minus 15. So 2 minus 15 is a minimum. In fact, a local minimum. And when x equals minus 2, we have minus 8 plus 24 plus 1. So minus 8, we have minus 8 plus 24 plus 1. So that will be 17. Y value will be 17 at minus 2. And minus 217 is a maximum, a local maximum. Now let's look at another example. Find the nature of all stationary points of the curve y equals x cubed. So let's differentiate y with respect to x. We obtain 3x squared. So dy dx is equal to 0 at x equal to 0. So we have a stationary point at x equal to 0. So let's draw x equal to 0, dy dx is 0. So on the top we have the values of dy dx, on the bottom we have the values of x. So for a number less than 1, for instance minus 1, dy dx, so if we substitute minus 1 for x, we have plus 3. So it's dy dx has a plus value, positive value. For values greater than 1, for x, dy dx is positive. For values less than 1, if you substitute for x in this expression, we still get a positive value. So the sign of dy dx does not change at the stationary point. So clearly this is a point of inflection. And let's check, let's do the second derivative test. So if we differentiate dy dx once more, we'll obtain d squared y dx square is equal to 6x, and at x equal to 0, the second derivative is 0. If you substitute x equal to 0 in here, we obtain the second derivative equal to 0. So clearly x equal to 0 is a point of inflection, and when x equal to 0, y is also 0. So we could write 0, 0 is a point of inflection.